Well, if we're doing a titration of a weak acid with a strong base, this means this must be in the flask and this must be in the burette. So when we're looking at the titration curve, it'll look like this. And if it's pH, then it's going to be little p, big H. And what are we adding? We're adding the base. So it'd be volume of KOH, because we're titrating this with this. Alright, so we're looking at what we're starting out with. We've got a weak acid. We'll start out at a pH of about 5. And then we will draw our curve. And we'll end up with a pH of about 13. And that's because we're dealing with a strong base, so all that's going to be left after the equivalence point has passed is just going to be the KOH. The other thing we want to look at here is whether or not we're going to obtain a buffer region. For more information about this, I really want you to go back and take a look at my other mini lectures that indicate when a buffer region is going to occur. So let's look at what's going on here at the very beginning. What we might have is, let's say we've got just this weak acid, and I'm going to call this AH. And let's say we've got 4 of those present at the very beginning. Now what's going to happen is, just as a general reaction, the AH will react with the OH minus, and what we will have is A minus plus H2O. Alright, so the AH is going to be this weak acid, the OH minus is going to be the strong acid. Now if we react 2 AHs with 2 OH minuses, that is, we're just going to add in 2 OH minuses, what we'll be left with at, say, this point might be 2 AHs, and then 2 of the AHs we originally started with will turn into A minuses. So what we'll have in the solution at this point is a mixture of AH and A minus, and that would be a weak acid, because that's what we're told, and its conjugate base. So indeed we do have a mixture of a weak acid and its conjugate base, and what we are going to see is a buffer region, because that will indeed resist changes in pH upon the addition of this strong base here. So we have a buffer region here. Okay. Let's look at the reaction showing the main products in solution at the equivalence point. So we'll have the acetic acid, the weak acid, reacting with the KOH. So we'll have equal amounts of these at the equivalence point. And what's going to happen is that since this is a weak acid, we know it's going to release an H, that'll be as H+. And since this is a strong base, we know it's going to release OH, and that'll be as OH-. So these two will join together and form water. So we know that that's one of the products. And whatever else will combine together and form the salt. Now this particular salt is going to be a weak base. So let's see how that gels with the equivalence point. We know that we can estimate the equivalence point by averaging the starting and finishing positions. So it'd be 13 plus 5 divided by 2. which is going to equal 9. So we look at this, we see this as a weak base, and that matches with what we're getting for the equivalence point, which is about 9. That's where we'd expect a weak base to be as well. So when these added together, we got the H plus combining with the OH minus. This effectively is PHCH2COO minus is what this will end up being. And that's reacting with the K plus, and that's how we're getting those two things to join together. So that's the final answer right there. You don't really need to show this. I'm just showing you where those two things come from. Alright, so that's how you get that reaction. And now we can answer the other questions. Starting pH, well, since it's a weak acid at the beginning, it's going to be 5. Ending pH, strong base being added, so it'll be 13 at the end. And which indicator do we use? Well, we use the indicator that will best describe what's going on at the equivalence point, and it will cover that region. So this would be a pH of 9, so I would choose phenolphthalein as my indicator for this one.